Welcome back. We are in 4.4 and today we will continue with some more optimization problems. These things are a little more interesting, I think, and they're definitely more geometric. In this example, a rectangle has two sides along the positive x and y axes, one corner at the origin and the opposite corner on the parabola, y equals 12x minus x squared. Find the width, height, and area of the largest such rectangle. So just looking at the picture, I see it looks like I have x along the horizontal and I have y as the vertical. So that's the height and width of my rectangle, the y and the x. And there's this opposite corner, and the opposite corner of the rectangle can be any point on the parabola. And at various points, the rectangle will look different. I have a little animation that will show this. Here we go. So this is the program called GeoGebra. And when I move the point, different rectangles result. The rectangle might be very small. It might have a very small area. Then the area grows. And then the area shrinks. So we want to know where should that point be placed on the parabola that gives us the biggest possible area. So what are the objective function and the constraint? Well, the objective function is what is it that we're trying to maximize or minimize? In this case, area. Area of the rectangle, x times y. So A is xy. What about the constraint? What are x and y constrained to be? I can't just make x as large as I want and y as large as I want. They're constrained by the fact that the opposite corner lies on the parabola. Well, that opposite corner has coordinates x, y, x to the right and y up. And I know that every point on the parabola has the equation satisfies y and x is y equals 12x minus x squared. So that equation for the parabola turns out to be exactly the constraint that we want. What happens next? Next, I need to get my objective function into one variable. The constraint is already solved for y, so I will take this whole 12x minus x squared and substitute it in for y. When we do that, we end up with a function of one variable, x, and that function is 12x squared minus x cubed. Now what do I want to do? Right, we'll take a derivative of a. So a prime, turns out, is 24x minus 3x squared. Now what? Let's figure out where a prime of x equals 0. We'll solve a prime of x equals 0. Now I have here that it says that the answer is either 0 or 8. Let's just check that to be sure. So solve a prime of x equals 0. So that, in other words, 24x minus 3x squared equals 0. I can factor out 3x, and that leaves me 8 minus x equals 0. Yeah, so it looks like x equals 0 or 8. Well, what's the answer? Is it 0 or 8? I didn't expect to get two answers. So let's go back to the animation. And when my x value is 8, well, that certainly looks like a very large rectangle. And when the x value is 0, that'll give me a min. So the problem doesn't really know that I'm looking for a max. When I solve a prime of x equals 0, it'll give me a place where the derivative is 0, but that 0 could occur at a min, or that 0 could occur at a max. So it's up to us, when we get two answers, to look at the problem, think about the context, maybe do a little more math if you need to, and realize what is the answer that we really want. So for us, x equals 8. We also wanted to find the height, so now that I know x equals 8, I could go back to my constraint and figure out y. So it turns out that y equals 32. And once I know x and y, I can figure out the total area, 8 times 32, which is 256. So that solves example 1. One more example. In this case, we have a point on the line y equals 6 minus 2/3 x. And this point, can move anywhere on that line, and I want to find what is the point that makes the segment from the origin to the point as small as possible. Once again, another animation. There's the point on the line. I can drag the point. Sometimes that line is long, and then it's short, and then it becomes long again. So where should I put the point that makes the segment as small as possible? So as always, we have an objective function and we have a constraint. I've already put the objective function down there for you. The objective function is simply the distance from the origin to the point on the line. So you can think about this as the Pythagorean theorem. I have an x and a y, and so the hypotenuse will be the square root of x squared plus y squared. There's the distance. And my constraint is that the point xy has to lie on the line, so y equals 6 minus 2/3 x. Now, I'm going to do something I haven't done before in any of these problems. I'm actually going to change the objective function a little bit. Because for the objective function, once I substitute, I'll have to take a derivative. And this looks like it could be kind of a messy derivative. So here's a trick, and it really is just a trick. Instead of using the square root of x squared plus y squared, when you have distance problems, it's often nice just to use x squared plus y squared. Because think about it. When x squared plus y squared reaches its smallest quantity, then the square root of x squared plus y squared is also as small as possible. So if I can make e as small as possible, then automatically d will be as small as possible as well. And it's just a little bit easier to work with e. Alright then, what do I do next? Let's make my objective function into a function of one variable. I can take my constraint and substitute in, and doing a little bit of arithmetic, we find out that e of x is 13/9 x squared minus 8x plus 36. Now what? Take the derivative. Now that I have the derivative of e, what's the next step? Now I want to set that thing equal to 0 and solve. Solve when is the derivative equal to 0. And it turns out, again, just a little bit of algebra, the derivative equals 0 when my x is 36/13 and when y is 54/13. Alright, that's it for some of the more interesting geometric optimization problems. Think about these problems, give them a try, complete the worksheet problems, don't neglect that. Do the homework, and as always, please let me know if you have questions.